there is this phrase called the loyal opposition. So I think Marco Aurelio invited me a few years ago, before deep learning was really hot to speak at a workshop. Then very recently, when this deep learning craze was sort of just starting off but not really caught on, one of these days I got a phone call from Jeff Hinton in my office saying, Jitendra, I believe you don't like deep learning. So I said, oh, so you know, what do you say? I said, yes. There is this British way of sort of extending things out where a yes actually means no, or it leaves it intentionally vague. So he said, why? Why do you not like it? I said, because you haven't proven your point. And you work on data sets like CFAR, which, as far as the computer vision community is concerned, are like tiny and kind of out of the way. And you will only convince us when you do something serious. So I said, so he said, OK, what is something serious? I said, OK, try Pascal detection. So he called me back the next day and said, no, that doesn't have the right kind of data. What do you think of ImageNet? So I said, OK, that is solid. I will believe that. And so that is my little role in the current resurgence in deep learning. However, what I want to do is to really actually talk about vision as a whole and the big strands in a historical way. I believe in this line from George Santayana, those who don't know history are condemned to repeat it. And I think that historical view will also situate the big ideas in vision. And we'll find somewhere a role for deep learning. OK, so this is kind of my favorite talk these days. I talk about vision as composed of 3 processes. OK, I need a pointer. Is there a because I can never use the mouse effectively. OK, with this thing? Which one? This one? Oh, yeah. OK. OK, this will not work too well. But OK, so there is the task of recognition, which we all know, which is assigning labels to objects. There is the task of reconstruction, which traditionally means recovering geometric shape. But in my definition, it also includes recovering reflectance, lighting, and so forth. And then there's the task of reorganization, which people would call grouping or segmentation and so forth. I call it reorganization so that everything begins with R. And I can call this slide the 3 R's of computer vision. The basic. This is a back projection, so they cannot actually see the point. OK. I'll just use my hands. OK. The big picture that I would like to claim that I would like to make is that, in fact, these 3 modules are coupled to each other. Historically, we have worked on each of these modules as silos. But I think the amount of progress that you can get from that is going to hit diminishing returns. In fact, here are 3 nodes. And in each of these, then by connecting these 3 nodes, there are 6 arcs. And my point is that there is useful information to be communicated across each of those 6 arcs. And through the talk, I'll try to make that point. So first of all, I want to just take the top arc, recognition, the top node, recognition. So I want you to have a view of what the richness of the problem is, because very often you'll see talks which hit a specific problem. And that's fine. But what's our grand goal? So a grand goal, this is a slide actually from Lubomir's thesis talk, if I remember correctly, that I stole. This is what professors do. They forget how to make slides and they just steal them from students. So there's the task of object recognition, which is kind of the Pascal task. Put a bounding box around each object. There's the task of semantic segmentation, finding the pixels of each object. There's estimating pose. There's recognizing action. There's attribute classification. And at the end of the day, this is what we want to do. We want to generate pretty rich descriptions. And there are applications which would rely on this. And I want to put up this slide, which I like a lot. This is work from Feifei and Perona, which was a psychological study. They showed an image for very short periods of time or for medium periods of time and so on. And then when the image was taken away, people were asked to describe what they saw. So with very brief exposures, you just get sort of splotches of color. But for longer exposures, like 500 milliseconds, you have people writing things like some kind of a game or fight, 2 groups of 2 men, 1 in the foreground, blah, blah, blah. So it's practically like writing a novel. So whenever you hear a talk on recognition, you should ask the question, is it ready to achieve this level of description? Because that is our goal. So yes, we are going to start with smaller steps, but keep in mind the grand goal, and the grand goal will force you to think about the problem in its greater generality. Okay, again, I'm going to take this historical perspective, and in particular for deep learning, a lot of the insight and intuition has come from neuroscience. So it's worth sort of seeing these three angles of vision in general, not computer vision, vision. So vision has these aspects of perception, which are really behavioral studies, or where you show people an image and you try to elicit what their internal percept is. There's neuroscience, and then there's function, which has to do with the fact that there are these constraints which come from the laws of optics and natural image statistics. The connection between human vision and computer vision is strongest at the level of function, but we have historically relied a lot on insights from perception and neuroscience. In fact, all the big ideas in computer vision, they can be traced back to big ideas that originated in the history of perception and neuroscience. So I'm going to take you through some of those, and hopefully that will enable you to see the current situation better in context. Okay, so let's start with neuroscience. Okay, so this is work from Hubel and Wiesel. It's now, I guess, 51 years old, and in fact, I think David Hubel died a week ago. So, and they got a Nobel Prize for this work in the 80s, I think. So they discovered orientation selectivity in V1, which is kind of the first stage of visual processing in the brain. And the slide shows that there is this bar, and if it's at the right angle, you get lots of spiking. And if it's not at the right orientation, you don't get lots of spiking. And you have various kinds of cells. They are simple cells which respond to edges or bars of different polarities, different orientations, and so forth. And then there are so-called complex cells. And the property of complex cells are that if you move the bar a little bit, it doesn't matter, the response is still high. So that was simple cells and complex cells. So this idea, which really is 1960, I think this is behind the design of all the convolutional neural nets, which I regard as the most concrete example of deep learning. But it really goes back to Hubel and Wiesel. And of course, many people have used this basic insight from neuroscience that the first stage of visual computation is orientation selection. And SIFT and HOG and so forth, they're all built on this idea, because you have a cell, and in that cell you have some orientation. You don't care about the precise position. That's the idea of having a complex cell. Okay, so now you can put it in some computational form and you get orientation histograms in a block. Well, you've got SIFT and you've got GIST, and all of these are variations on that theme. So it's worth noting that the mainstream computer vision features are in fact derived exactly from this insight, which goes back to Hubel and Wiesel. But we know more from neuroscience, and we know from neuroscience that there is more to vision than V1. There are many layers, and this is a slide which shows the areas of visual processing in monkey's cortex. And actually, the work has got to be pretty elaborate, and you have these diagrams for different areas of the brain, and they look kind of like a set of chips and circuit diagram with various layouts and so forth. So we know a fair amount, but we don't actually understand the mechanisms very well. We understand them at the earliest stages. We know roughly what's happening in retina, LGN. V1 is maybe mostly understood, but never fully understood. And as you go higher up, there is a fair degree of vagueness. As you get to something like inferotemporal cortex, there's clear evidence that there are cells which are sensitive to faces and places and many interesting semantic categories that we are interested in. But we do not know enough about the neuroscience in detail. So I want you to keep this in mind. We are operating, when we try to take insight from neuroscience, we do not really know the neuroscience well enough. Maybe we know 10, 20%. So the way you get insight about this is go back into the history of science. If you were in the 19th century, for example, there were these debates about the history of the Earth. And there was evidence from fossils and so forth, which was leading in a way where the physicists were unhappy because they couldn't think of energy. So there were arguments from energy production. And they were basically wrong at that time. Okay? The empirical people were right and the theoreticians were wrong because they didn't know mechanisms of sort of radioactivity and so forth, these various processes which happen in the stars or inside the Earth. The physicists have no clue of this. So in fact, the theoreticians were wrong and the empirical people were right. And I think that there is a lot of that which is going to be the case in neuroscience. We know very little. So to build a full theory on the basis of your current knowledge is, I think, foolhardy. Just use the insights, but approach your state of knowledge with humility. Okay. So, but now that I've put in that caveat, and keep that caveat in mind all the way through this talk, there are clear observations which suggest that from perception that the recognition process is mostly feed-forward. Okay, it's not fully. If there is evidence of feedback, we don't know exactly what it does, but feed-forward can do quite well because there are studies which show that you can get recognition or signals corresponding to recognition in 150 milliseconds, and the synaptic delay is say 20 milliseconds, or 7 synapses. So you haven't had time to do much feedback processing. So, so this is correct. And so naturally that suggests that we try to build an architecture which is more or less feed-forward and see where it goes. And obviously Hubel-Wiesel really said this. I mean, they had this architecture. They were not computational people. I think the most explicit computational statement is from Fukushima in this paper from 1980. And he has, if you see S's, and so there are simple cells, complex cells, simple cells, complex cells. You will see this reoccur in Jan LeCun's convolutional neural nets, but Fukushima had this core idea. And I mean, this was around in the 1980s, I would say, because if you were a person interested in computer vision or machine learning, but you were aware of the biology, you would know this. Okay, and then there is convolutional neural nets coming in at the end of the 80s. Okay. And Jan LeCun's contribution was essentially a training mechanism for these multi-layer networks. Okay, and that training mechanism was backpropagation, which had been invented. Well, it had been reinvented because all good things are invented multiple times. Okay, and this is a paper, and I've actually clipped out this. This is an entry from Google Scholar, which sort of has the year and the citation count and so on. In fact, this is the original paper. Most people seem to cite the 98 paper, but this is the original work. So I prefer to do this to give an appropriate historical perspective. So you've got essentially simple cells, complex cells, and so forth. But what Jan does is, and his colleagues do, is essentially they do backpropagation. So it's a multi-layer perceptron of a certain type. Now, most of you, maybe 99% of you, were not around at that time, or if you were around, you were babies or something. Okay, I was, right? I mean, I remember this first neural network wave, and part of the excitement was that this ability to train multi-layer networks. And then LeCun's contribution was to restrict it. Instead of taking a multi-layer perceptron with no constraints, he put in constraints which we know are very sensible for vision. So the thing to note here is, it's not, I think it's a myth to say, oh, in this, once you have deep learning, you learn everything. No, you don't learn everything. You put in your effort in designing the architecture. And all your insight goes into designing the architecture. And if you design an architecture well, then it will learn interesting, useful things. I want to point out another paper from that time. This one is from Pietro Perona and me, which is also exactly that era. It's also, I mean, I think our conference paper was 89, and this network is this is an example which shows how different ways of thinking can come to some similar conclusions. So we were trying to solve the problem of pre-attentive texture segmentation. This was an open problem at that time. So on the right-hand side, you see these texture pairs, and you have to split them. Okay, so we designed our network. We had no learning in there. And we designed it actually with tricks which have suddenly resurfaced in the neural network literature, because we had half-wave rectification, which Jeff Hinton calls, what does he call them? Rectified linear. Anyway, the right term is half-wave rectification. Okay. We had because it goes back to the E literature of diodes. I mean, I think that's because you can't be rectified and linear at the same time. So that's a contradiction in term. I think my term is the right term. Okay, we had max pooling. Okay, you can see that at the top. So this is actually a picture from that paper, max something something. And we actually had competitive sparsification in some hacky way. But it was completely hand designed and it did not bother us at all. Okay, but and the reason was we wanted zero-shot learning. We needed it to work pre-attentively for any textures that were displayed. And we could not have, I mean, the whole thinking was that's what happens in perception. You don't want to be training to particular textures. Okay. So, and this is, yeah, so this is a paper from that era, and it's also about that cited. So, okay. Now what happened? So you have this mode of operation. And then the question is, what's happened in the last 20 years? Okay, so because you have two examples of architectures reasonably useful for particular problems. I mean, well recognized. It's not that these ideas disappeared. So what's happened in the last 20 years? Okay. Okay. Neural networks required a lot of black magic, and I think they still require a lot of black magic. Okay. And I think that Marco Aurelio's talk, I mean, he did, I think, an excellent job of sort of exposing what are the tricks of the trade, but the fact remains that there are tricks of the trade. Now, you could say that, look, if you want to be a car mechanic, you have to know something about how to operate, you have to know what you're doing, and that's fine. I kind of accept that. Maybe there's an irreducible amount of knowledge, but I think it's a fact that novices don't find it easy to make architecture and parameter choices. And the contrast is with some other learning techniques which kind of came to the fore in the 90s. Support vector machines is one of them, classification and regression trees. The current version is random forests are examples of these. These are much easier to use. And I can say this in a scientific way because I've taught computer vision and machine learning for many years. And I have used our undergrad AI classes. I have tried homework problems where people have to train a convolutional neural net or they have to train a support vector machine. Support vector machine is very idiot proof because all you have to do is to get one parameter right, C. Okay? Okay, you can get that right. I mean, okay, well, there's a lot of stuff to be done. So I think it was never, I believe it was never the case that, and I mean, LeCun says this and I agree with him. It wasn't ever the case that SVM suddenly could do things that neural networks could not. I think that, I mean, LeCun always had the numbers. Okay, it was not that SVMs beat out because of better numbers. No, that was not the case. They beat out because of simplicity of usage. Okay. I think there are some cultural factors too, which is that around that time, the NIPS community got in bed with the statisticians. Okay. And once you had these statisticians and convex optimization people, these are people who like certain things and don't like certain things. I think the old neural network spirit was kind of like, you know, it was like engineers, hackers. I mean, we'll do things. If they work, we are happy. We don't care about, you know, some highfalutin theorems and all the rest. Okay. What we care about is does it work? And I actually respect that spirit. I mean, this I like. I think that in recent years, NIPS has kind of gone down this path where they've become a bit too solipsistic. And so in this sense, I like the deep learning crowd. They'll shake up that otherwise you can become sort of this navel-gazing community where you're proving these theorems which nobody else cares about. Okay. I like the adventurous spirit of the neural network crowd back from the old days. So this is why even though we disagree on many things, I'm very friendly with both LeCun and Hinton because we have these conversations. They are totally willing to step outside the bounds of what is mathematically respectable. I think it's a good thing. I encourage all the youth of today to keep that in mind. Okay, computer vision community, what happened? I think like kind of the first 2-3 arguments apply. The computer vision community, there was some work on neural networks in the mid-90s. I think many of you don't know that like the first decent face recognition system was this sliding window paradigm with Rauli Baluja Kanade. And this was a, I don't know, one of them might be, is Rauli in here in the audience? No, okay. So, I mean, and that was a neural network. Okay. But then quickly, we basically all abandoned this and got onto the neural network, to the SVM bandwagon. And by the way, I should say, in the SVM business, a lot of the propaganda for SVMs is the kernel and the kernel trick and all the rest. In practice, we never do that stuff. Okay, so I think that generality of the, because we can't afford it. So when you do sliding window detectors, you use linear SVM. So in that sense, I think the critique from the deep learning crowd that it's very flat, it's very shallow, is valid. In principle, kernels get you out of that, but we can't afford fancy kernels. So this is reality. Okay. Okay, so the computer vision community, okay, this slide is, maybe you all know this, but I think it's also worth noting that the computer vision community in the 90s was mostly not doing recognition. They were mostly doing geometry. And then there were significant advances in the 2000s. And some slides, so a couple of slides on what strands went through the computer vision community. So how am I doing for time? When do I end? 12:30? I have that many to go. That's how much left, right?
Was questions or without questions? Including questions.
Okay.
That includes questions.
Okay. Good. Thanks. No problem. Okay, so see, these are some of, like, I have a couple of, obviously a biased view of history, but things which came about from Berkeley are overrepresented here. So these are ideas like the bag of words. I think this is the earliest paper on the use of bag of words for computer vision. There is Lazebnik, Schmidt, and Pons, which takes this bag of words idea but adds spatial structure. This was very effective, and it went together with SIFT descriptors. There is Darrell and Triggs, who it took the idea of, I mean, it's kind of like SIFT, but generalized a bit and used as a basis for a detector. And then there is the work of Felgen, Schwab et al., where in addition, so you don't just have one Hog template, but multiple Hog templates. And I think we have made a lot of progress in this paradigm. So it's easy to, now we will be critiquing it and saying, okay, why limit yourself to just orientation? That's essentially using the features from V1, and why not use features from multiple layers? But it was, I think, a great thing that we stopped feature munging around somewhere in the mid-2000s, because you can keep playing that game in various hackish ways. What we did as a community was we focused on the later stages, and we learned a lot about those later stages. And I believe that those insights are going to be of full value unless you are extremely religious about the structure of your network. If you are going to be open-minded, you will find that a lot of what has been done in computer vision is very relevant. And there is the Pascal challenge, and okay, I have to put this slide up because so that Lubomir is happy. Okay, so this is a better part detector. I actually think all these ideas are totally relevant in when we swap one feature machine with another feature machine. Okay, where are we now? So I think the computer vision community for a long time has been, quote, stuck on SIFT and Hog. And it was probably a feature at a while, and at some point it becomes a bug. Okay, and these are, okay, V1 inspired features, but there are clearly more layers between V1 and IT. Okay, I am, my second statement is my acknowledgement of what I think the way in which I have changed my mind post the success of Krzyzewski et al. On ImageNet. I think that earlier this claim had not been made in a solid way, but now I think there is experimental evidence that convolutional neural nets can serve as a feature learning machine. The third statement is my assertion that I don't think that it is uniquely convolutional neural nets. I think the issue is really high capacity in the machine learning sense. So in machine learning, there is this so-called bias variance trade-off. And you have some notion of capacity. VC dimension is one measure, but there are various ways to think about this. If you have little data, You should stay with low capacity. At that point, you will have some bias, but you'll have low variance. That's a wise thing to do. Okay, if you are as you have more data, you should increase the capacity of your network. This will lower the bias, but the variance will not go up so much because you have enough data. So this is a basic point. There's a classic paper from Stu Gieman, which everybody should read, which I always conclude my machine learning class with that lecture on the bias variance trade-off. So I think that's done here. I think what Krzyzewski et al. And Marco Aurelio and all the people in this movement deserve a lot of credit for is totally putting their feet on planting their feet and saying, okay, we have a lot more data, let's use high capacity networks. They may not have given exactly that argument, but this is how I will rationalize their line of work. Okay, but the last point, which I'll try to quickly sketch, is that features are just one component of a recognition machine, and recognition is just one component of a vision machine. So it's a little bit like, I guess today's analogy would be, if the Republicans in the House who only control half of one of three branches of government think that they should have their full say. It's slightly off, right? So I think there is some role for features, but it is one component of a bigger machine, and I'll try to show you a few examples. So let me first try to back up this claim that I think many architectures will. This is a prediction, so I could be false. So you can, if 5 years from now, this is not true. I'm making a falsifiable statement. My assertion is that what happened with handwritten digits will happen with more bigger data sets. So in handwritten digits, the first impressive results were from Jan LeCun. But over time, basically any decent classifier, okay, with a variety of features, has managed to get under 1%. So there is CNNs, there is tangent distance, which is a nearest neighbor technique with a clever metric, randomized decision trees, which now we are called random forest. This is shape context matching from our group. There's also a nearest neighbor technique. And you can do this with orientation histograms and SVM, linear SVM. So there's like 6 ways to skin the cat. I mean, okay. I think the main thing is you need to have enough capacity. And if you have enough capacity, you will be able to train your learning machine. Okay. Way forward in recognition. Okay, I'll state a couple of points, and then depending on the time, I'll back them up. I think that it's a lot. We should make use of lots of data, but at the end of the day, we also need to deal with little data, because we all know that pretty much all the frequency distributions of any category across categories, they all have this phenomena of heavy tails, and I mean that's where you are judged, how well you do on the heavy tails. And for the heavy tails, you're not going to have too much training data. So the important thing is how much of a generalization you have built up from the common stuff to deal with the uncommon stuff. I think that is the challenge. You need to be able to learn from very, very few instances. I mean, single instances ideally. And this was, I think, going to be partly clever generalized features, but I think it's also going to be based on things like insights that we have from child development, such as so-called shape bias. So children have, with very few data generalized, and they have this bias that they will care about the shape and less about color and markings and so on. Top-down, I think the recognition problem itself has these components of recognition, key point prediction, and segmentation, and we need to treat them together. Recognition and figure ground inference need to co-evolve. Occlusion is signal, not noise. Okay, now here I have a demo which I want to you do. Okay, is the audio on or? Okay. Maybe it doesn't matter. The music is not so important. Okay. Is there?
Muted on YouTube.
Oh, I see. Okay. Oh. Okay. So so I think the point of this is there is what you see here is a conflict between top-down classification knowledge, where once you know the head, there is a segment, there is a classification. Your classification engine would parse the person according to that. But no, this is getting messed up by the fact that there is a low-level signal based on continuity of brightness and common motion. And so this is an example where this is a category you know really, really well, I mean people. And yet the bottom-up signal of continuity of color and common motion is messing up your interpretation of this data. Okay, so this is, okay, so how do I get back? Okay, I'm on. Oh, is it? Oh, yeah, thank you. Okay, so how much time do I have? 7 minutes. Okay, including questions. Okay, so so super fast. Okay, so okay, so I said this already. All of these directions are useful. So let me give some examples. Okay. So this is an example of recognition helps reorganization. So you're vision people, so most of you have seen this. So here's an image where it's the recognition which is driving segmentation. Okay. Here's an example where recognition helps reconstruction. So this is an old paper from Blanz and Vetter, 1999. And so just examples of the coupling. So I just want you to see that the feature business is important, but it's a part of the whole story, not the whole story. The black and white tight stars, I already did this. Okay, let's just go through it very quickly. What are other big parts of vision? Okay. There's optical flow. Okay, why do I put this up? We use the insight from humans about the various layers of processing for recognition. But what is common to any animal that has vision? Every animal that has vision has motion perception. And that motion perception is based on optical flow and navigation. And you have this in flies and birds and everybody else. It's the most basic module in perception. Okay, so is this, and the neurons for this have been well established, etc., etc. Any story that we construct for vision has to have a big component around this reconstruction of three-dimensional space for navigation and moving about. I mean, should we forget about this because now we have convolutional neural nets? Okay. Should we forget about this because we have convolutional neural nets? Should we forget about doing 3D reconstructions of buildings? Should we, what about all this? These are major successes of computer vision, and I think if we want to consider the whole story, this is going to be part of it. I'll give you another example. This is closer to my heart in recent times, which is, it's not just reconstruction. We can make these clever interpretations about what is a surface marking, what is a shadow, what is, and all that. And how do we do this? So this is like the 30-second view of this. This is work with John Barron, who's in the audience. So we are trying to solve this problem of, given a single image, how do you infer what was the albedo, what was the shape, what was the lighting which gave rise to this image? And here's a demo which shows this. So the input is just a single image, and the output is everything on the right. So the input is just that top left corner image. How do we do this? It's some statistical story. And so this has all got to be part of our understanding of vision, some kind of Bayesian inference where we are trying to say what images, what worlds are most likely given the image that we have seen. And okay, so this is one strand that I wanted to point out. Another strand, this is the strand on reorganization or grouping. So the Gestalt grouping factors, so this is work from the 1920s, and they pointed out how the Gestaltists were very clever, and they knew about the role of recognition and top-down knowledge. But what they said was, how is it that the entities are produced on top of which memory can operate? And there had to be something which was a precursor. So the setup of supervised learning is very non-biological. You don't have this kind of input in biology. That's why, in fact, part of the motivation for the research in unsupervised learning has been motivated by that. But in my view, unsupervised learning is kind of gone off on this tangent where they have ignored the issues of grouping, which to me is the central way in which visual perception works. So unsupervised learning should really be about learning grouping. And this is a phenomena for perception in general. Okay, but that's a topic for another time. I wanted to point out that there are lots of insights from child development, and there's a very rich literature. There is Liz Spelke is one of the heroes in this business, and so at a certain age, at 4 months, children will group based on common motion, but they will not group based on continuity. But 5 months, at 5 months, they will. This has all been studied. Okay, so think about how children acquire language. They do not acquire language by watching TV. At least I hope that those of you who are parents will not subject your newborns to that experiment. Okay, they acquire by interaction with the world. There is a certain, so a child growing up trying to acquire knowledge of various visual categories has access to this basic machinery for grouping, which they can build on. And there are some examples of work, which this is again an example from our work, where if you want to find this cat, you have to do a combination of bottom-up processing as well as some top-down templates. And okay, everybody has numbers. Okay, you can now that you have data which is Connect type data, we should use this because this is a good example where we can do reconstruction, reorganization, as well as recognition in this framework, and this leads to some results. So this is my concluding slide, and I'm happy to answer questions.
Thank you. I really like the part of your talk where you said you should question assumptions because we don't really know, the details. But then you made a pretty strong assumption. You said, well, recognition is feed-forward. And how do you know? So the question is, how do you know that it's not a feed-forward feedback system that doesn't have to do a lot of feedback to do the recognition of the patterns that you're able to do relatively quickly? And how do you know that the mask that they use for the patterns is not dissimilar?
Yeah, so let me answer that. It's an assumption, and I don't necessarily believe it fully, and but I think it's a plausible hypothesis. And this plausible hypothesis has driven the design of networks like the convolutional neural networks, and that's perfectly good. See, ultimately, when we can take insights from biology, and we don't need to be accurate to biology. We can then judge it on engineering criteria. And it's a plausible hypothesis. I doubt that it's the whole story. But look, we always see through a glass darkly, right? There's this line from statistician George Box: all models are wrong, but some models are useful. Okay, remember, it's an imperfect process. We know little. We are on a journey. We will know more. 2 years from now, we'll know even more. If anybody says that they know the whole story, he's either a fool or a charlatan. Okay.
Questions? Yeah. So, please give him the mic.
I like the story, but I've never seen a good architecture that will do any of this. So we have feed-forward recognition.
Okay, I've never seen an architecture that will do this. So it's pretty much concentrated on feed forward, and you know, the answer to the other thing is the propagation delays in your brain mean that a lot of what we see is done in a feed-forward pass, and then maybe all this, that filling in of that diagram is done with the feedback of like the time delays of 50 milliseconds, 80 milliseconds. But I've never seen any architecture that can do this. And I don't know if you have insights about what might do that.
I don't have such an architecture either. I mean, I think that there are always proposals. I mean, like I think Jeff would argue that one of his networks does this and so on. Every 2 years, Jeff has a new model, and it's the new story of what the brain is. Okay, so I think so. My own style is, instead of the grand architecture, I want to solve littler problems. So if I want to understand, like for some years now, for like 15 years, my dream has been to understand the relationship between recognition and grouping. I'd be very happy if I can do that. So we do it bit by bit. So here's a historical analogy. Think of electricity and magnetism in the 19th century. So you had people like Ampere and Ørsted and Faraday and so on. There were these intriguing phenomena. There was magnetism, there was electricity, there were some connections, something could cause this, but nothing was clear. Finally, it became totally clear when Maxwell had his equations. And now suddenly you have this beautiful unified system with, it's just so pretty. But it took 100 years to get there. And their problem was so much easier, right? I mean, I have this line that I often use, that God must be a physicist because she gave them all the easy problems, okay? So, you know, our business will take time. And in the meanwhile, instead of a very, so I mean, this is vague, right? This is just like bubbles and arrows. I mean, it's not much better than that. But I like these bubbles and arrows because it makes me think of the right problems, okay? And I will work. I cannot publish a paper in CVPR pushing this. I can only use this when somebody invites me to give a talk, so they can't throw me out while I present this. The way the field will progress is through concrete papers which are solving smaller problems. But it's good to have a bigger view.
Last question, okay.
So what is the next small problem in deep learning that we should solve to make a step towards the solution of the big problem? So what is the next target for us that you can suggest?
I think just a richer view of recognition. I think that's the most immediate goal. A richer view of recognition, which would include the following traits. One is some notion of localization. Okay, localization of parts, localization of key points, nose, elbow, shoulder, etc. And localization in the sense of pixel support. So I think there is some work in this direction. So Jans has done some little bit on semantic segmentation, but I think he has not adequately used the constraints which come from coherence of color and texture and things like that. And then actually understanding pose. I think that this is something which should be approachable given where you guys are now.
Let's thank the speaker again.
Yeah.